Good afternoon, everyone. Let's just wait a few minutes for others to come onto the call. I see the numbers still rising. Sorry, I think safe to start. It's 2:01. Good afternoon, everyone. To those of you who have joined us for last week, 2 weeks ago, then welcome back to the 5 series webinar on digital transformation for water and sanitation utilities. This is the second of a series of 5, and let me just remind you of the dates. Just a minute. Of the dates of the webinar. Today is the second of a series, and we hope that you will join us for the 3rd, the 4th, and the 5th on those dates as shown on the screen. We have with us 2 speakers today, both from Xylem. They will be introduced properly in a few minutes. But before that, I wanted to discuss a little bit on Zoom. For those of us who are new to the platform, there are ways to engage. There's a chat box at the bottom of your screen and the question and answer box on the right side of the bottom of the screen. For Q&A, of course, please use the Q&A box. And if there are technical issues that you wish to raise for WaterLink specifically, if there are audio problems or video issues, do use the chat box. In either case, we will be monitoring both boxes, so no worries on that. Do stay till the end of the session because we will also have a summary and closing remarks. Before I start with our first speaker, I'm so sorry, let's start with a poll. We encourage you to please participate at the poll to understand who you are, who is with us in the audience today, and it will also help us improve on our webinars in future. So Jazz, please launch the polls. We have 5 questions, and I encourage you all to answer the questions. We are giving you 2 minutes to respond. Okay, poll is ended. So can we have the results? Please share the results. We have mostly male participants, although quite a number of female as well, most in the age of 30 to 40, from government and private water and sanitation operators. Even split between the executive and the mid-level, and a little bit less on the technical. And of course, expectations, you have identified all of these. Okay, so without further ado, let me now introduce our first speaker. Our first speaker is Martin Shaw. He is the solution architect for Xylem. He has over 25 years experience in non-revenue water management and has worked in several projects across the UK, Malaysia, and Australia. Martin is no stranger to Asia, having worked on one of the first performance-based contracts in the region, actually in the world, to reduce non-revenue water for the state of Malacca in Malaysia in 1997. Sorry, the state of Selangor, my mistake. He is currently based in Kuala Lumpur. Martin, please, the floor is yours.
Okay, thank you, Mai. Let me try and share my screen. Okay, how are we looking? Okay, I assume everybody can see the cover page. If you can't, I'm sure you'll let me know. So let me kick off by saying thank you, Mai, for the introduction, and welcome to everybody. Thank you for joining the second webinar in the series of 5 on digital technology for the water industry. I'd like to firstly thank the 2 speakers we had in the previous webinar. They set the bar very high, so thank you for that. And I know Matthew and myself are looking forward to trying to make this webinar as interesting and informative as the first one. The title of this webinar is Detecting Leaks and Preventing Bursts the Digital Way. Let's have a look at the agenda. This is how we're going to structure the presentation today. We're going to be talking about leaks and bursts. So we'll start off by looking at the definition. What's a leak? What's a burst? And then we'll talk about the benefits of early leak and burst detection. Then I'll go on to talk about using digital technology to detect leaks, followed by a Q&A. And then I'll be handing over to my colleague, Matthew Kennedy, who will be talking about using digital technology to prevent bursts. Matthew will wrap up the session with a conclusion before a Q&A, and then he will hand over to Arjun for the closing remarks. Let's start off with a definition and have a look at what makes a leak and what makes a burst. I'm not going to read the text. I'll let you guys read through it, and I will talk in the background as you have a look at it. But this is the IWA definition taken from a recent publication of theirs. And what this shows you is that the definition of leaks and bursts are really separated by how quickly you have to respond. So a leak is when water escapes from the pipe, but it doesn't affect service to the customer, whereas a burst has some sort of supply disruption to it. So the way that I like to look at this is that leaks are proactive repairs. So you can plan them in, you can book them in, and the leak crews can go and repair them in their own time. Whereas bursts are reactive repairs. And you really have to drop everything and you have to get a crew out there to fix them as soon as you can. And we did have some questions in the previous webinar about digital technology. Why is digital technology important? Why should we be looking to embrace it? And so I've put this slide up early on so that we can look at the benefits of early leak and burst detection. And again, I'm not going to read through the list. I'll let you have a look at it. But I'll just highlight some of the bullet points. Again, referencing back to the webinar that we had a couple of weeks ago. One of the speakers there, Dr. Amit, spoke about Taipei, water-stressed island. They haven't had a water shortage for 17 years because of their proactive approach to water loss management. He also mentioned Paju in Korea, where their customers can now drink the tap water, which they couldn't do previously. So that is obviously going to benefit the corporate image of the utility that supplies the water. Coming down to bullet point 5, there is obviously a big difference between undertaking proactive and reactive repairs. And I'm going to talk about SA Water in a case study as we move towards the end of my section of the presentation. And of course, the last bullet point, last but by no means least, proactive water loss management strategy can increase revenue. Now this graphic shows the volume of water that's lost by a leak. And what you can see, there are two different factors. One is the duration that the leak runs, and the other is the flow rate. Now, there's not much you can do about the flow rate apart from implementing pressure management. If you reduce the pressure, you reduce the flow rate. The problem is that if you don't find the leak and fix the leak just by reducing pressure, you then make that leak harder to find, but it still keeps running. So what I'm going to concentrate on is looking at how we can reduce the volume of water that is lost through leaks by breaking the runtime into 3 different components: awareness, location, and repair. Awareness is the length of time that it takes a utility to become aware of a leak. Location is the length of time it takes to pinpoint exactly where it is. And repair is the time it takes to repair the leak once you know where it is. So I'm going to split this webinar up into those 3 different components, and we're going to have a look at each one. And we're going to focus on how digital technology can help to reduce the time for each of these components. Awareness is all about enabling technology. And for water loss management, the enabling technology is usually flow meters, pressure sensors, acoustic sensors. And we're going to start off with 2 scenarios here. First scenario on the left is where a utility has no sensors at all, no enabling technology. They have no proactive water loss management strategy. And the way that they repair leaks and bursts is when they're booked in. So when somebody tells them there's a leak, then they'll go and book it in. Now, the problem with this is obviously that leak could run a long time before it surfaces. It could be months, or it could be even years before that water comes to the surface. And in this part of the world, there's the added problem that we have. And if you look at the photograph on the left, you can see that currently that water is in the shadow, it's in the shade. As soon as the sun comes up and it crosses the top of the building, that water is going to dry up. And what that means is that during the day when people are around, there's nothing to see. And then during the night when the sun goes down, the water comes back to the surface. Now there is also the alternative, the opposite, if you like, to the sun drying up the water. We also suffer from wet seasons. We have monsoon as well. So if you have a couple of months of rain, then you've got absolutely no chance of seeing visible leaks like this. So particularly in this part of the world, relying on people to book in the reported leaks, the visible leaks, it could take an awfully long time for somebody to book them in. So under this scenario, you could be waiting for months or even years before this leak becomes made aware to the utility. The second scenario we're looking at, again, this company has no sensors in place, but they undertake a proactive, active leakage control strategy. And by this, they send leak teams out to survey their whole network at a certain frequency. So let's just say, for example, they survey the whole network every 3 years. What that means is that the leak inspector that you can see there walks down the road with his listening stick and listens for leaks. The problem with this approach is that as they walk down the road, they listen to a leak, they turn the corner, and then the service connection that they've just listened to could develop a leak. And that leak will run until either water comes to the surface and somebody books it in, or it affects supply to the property, or until the next survey is undertaken. Now, if you're running on a 3-year duration, that next survey is going to be in 3 years. Of course, alternatively, somebody could be walking down the street, the leak inspector could be walking down the street, and a leak could break out just as they arrive at that property, and they'll book the leak in, and that means that the awareness time is only 1 day. So when you take both of those situations as a whole, what that means is that your average awareness time in this scenario is half of 3 years. So you're looking at awareness time of 18 months. So it's better than the first scenario, but there's still an opportunity there to see if we can make it a little bit faster. Now let's consider DMAs, district meter areas. I'm sure most people who are listening understand the concept of DMAs, so I'm not going to explain it. But the function of DMAs is to measure the flow that goes into a certain area, and we monitor that flow on a daily basis. The enabling technology here is the flow meter and the pressure sensor that we have in the zone. So what we can see here, you can have a look at the flow and pressure graph on the right. And what you can see here is the flow and the pressure data is coming in to whatever system you have on a daily basis. Now, what you look for as leakage practitioners, and I'm sure that most people who are watching this webinar have already spotted this, when you're looking for your real losses in your DMA, you look for the minimum night flow, because the flow that goes into the DMA at night is usually made up mainly of leakage, usually. And so by looking at your minimum night flow, it gives you an idea of what your leakage is. So in this example, we have our minimum night flow running nice and flat for the first 7 days. And then after that, we can see for the last 3 days, something happens. There is a definite change in the flow of water going into that DMA at night. Now, you should never look at flow data in isolation. You must always look at flow data and pressure data together. And I've got a slide coming up a little bit later that shows you why. But in this case, you can see that the pressure, both before and after the jump, is exactly the same. So we know that step in minimum night flow is not pressure related. So it means that we have to look at something else. So it could be a burst, or it could be an increase in night consumption. We don't know. It could be an open boundary valve. But it shows us that there is something there we need to investigate. And now, because we have the data coming in every 24 hours, it means that our awareness time is now down to less than 24 hours. So you can see how we're adding sensors and we're bringing the awareness time. So is awareness time now 24 hours because we have DMAs? Well, it should be, but that's not always the case. And this is a great example here. Towards the bottom left of the screen, you can see the benchmark minimum night flow. And we went in, we set up a DMA, we undertook leak detection, found the leaks, fixed the leaks, and we got the minimum night flow down to 3.2 litres per second. We then handed it back to the client. And this was in around about September 2010. The client brings their SCADA online around about February 2011. And what you're looking at here is minimum night flows across around about 18 months. And it's very clear that you can see that even when the client started the SCADA, the minimum night flow has gone up already. And it continues to rise and it continues to increase until that minimum night flow hits 13.4 litres a second. And that's roughly 18 months after they'd started monitoring. So if they had been looking at this, they would have seen the minimum night flow go up and they could have gone in, they could have intervened, and they could have done something about it, but they didn't. And the question really is, why didn't they look at it? Well, there's a number of factors for that. One of the factors in this particular case is because they're looking at SCADA. And SCADA data is usually user unfriendly. There were no alarms set, so they didn't see that minimum night flow going up. So this is an example of how your awareness time should be brought down to 24 hours if you have DMAs. But if you have a large number of DMAs, and I know that some of the utilities in the region have 800 DMAs, 900, 1,000, even 2,000 DMAs. And if you've got an enormous number of DMAs to look after, how can you make sure that the minimum night flow is staying constant every night? It's just not possible to do it manually. And even with a small number of DMAs, it's becoming more and more difficult because the data that we're starting to collect now, we're talking about big data. There's a lot of information coming in every day. When I first started doing non-revenue water management, we used to get 15-minute values coming in, so that's 96 values a day we used to get in for a particular DMA. Now with the high resolution transient data coming in, we're getting 256 readings every 1 second. So we're getting more data coming in now every second than we used to get in a day when I first started. And it's just impossible to try and manage that data manually. So the way that we can do it is to bring in smart water platforms and let smart water platforms bring all the data in and do the analysis for you. Smart water platforms are generally data agnostic, meaning it doesn't matter what sensors you have in the network at the moment. You can bring that data into the platform and it aggregates all the different sources. So it brings in flow data, pressure data, level data, quality data, consumption, anything you want, you can bring it in all to one platform and it helps you see what's going on in your network. They're usually cloud-based, which means that you can log in from anywhere. Particularly important during this period of the pandemic. If you're in Starbucks, you can log on and you can have a look and you can see exactly what's happening in all your DMAs. And as you can see here, this screen, this part of the dashboard shows the water balance. So if you wanted to calculate the water balance for your DMAs, you can do it every single day. I know some utilities are looking at their DMA and every month they're pulling data into Excel and they're trying to run it in Excel. It's not making the most of the sensors that are in the system. And these smart platforms are designed to do all the hard work. But most importantly, if you have data coming in at high resolution, even data coming in at 1 minute values, then that means that your awareness time has now been brought down to less than a minute. So from starting off at being no sensors, and it could be years, we can now be aware of what's happening in our network within a minute. So that's talking about digital technology to reduce awareness time. And now I'm going to go on and talk about how to use digital technology to help us with the location time. And for leak location, there are two major factors. There are a number of factors that determine how difficult it is to find a leak, but two of the main factors are pipe material and pressure. Now this slide, the top right-hand side is the IWA leakage manual, and this table is taken from that manual, and straight away two things jump out. Firstly, if you look at the right-hand side of the table, you can see that for pipes over 400 mil, then the appropriate leak detection method is E, which is inline inspection techniques. So what the IWA authors are recommending is that for 400 mil and bigger, you go for inline inspection. Now, I don't have time today to look at leak detection on big pipes and leak detection on small pipes. So what I've done is I've put a reference at the bottom of the screen there to a really good webinar that was run on behalf of the IWA a couple of weeks ago by Ian Rogers and Mike Wigglesworth. And they looked at how you can detect leaks on big pipes and the importance of doing so. So if your water loss management strategy doesn't currently include big pipes, then I'd recommend you have a look at this webinar. It's really good. The second thing that we can see on the left-hand side of the table is that for all pipe sizes from 75 mil up to 400. And for all materials, there's only two different methods that are recommended. There is either gas injection or there is intrusive acoustic technologies. Now, because this is a digital webinar, I'm not going to talk about gas injection. I'm going to really focus on how digital technology can help us with the intrusive acoustic. And the intrusive acoustic is recommending hydrophones. So that's looking at pipe material and how it affects leak detection. And now we'll look at pressure and how it affects leak detection. You can see there very clearly, the way that the sensors detect leaks on the network is by picking up the energy that is released as the water escapes from the pipe. On the left-hand side, you have a burst, you have a leak under very high pressure. And on the right-hand side, you can see you have low pressure. And it's clear there that the energy released from a high pressure leak is going to be a lot more than that released from a low pressure leak. So what that means is that you're going to be able to detect leaks under high pressure a lot better than you're going to be able to detect leaks under low pressure. So what we're going to do now is we're going to add more sensors into our DMA. We already have the flow and pressure sensors. We're now going to put noise loggers throughout the DMA. And you can see that the graphic to the top left represents how the noise loggers are spread through the DMA. The photographs at the bottom show the different types of noise logger. So we have the accelerometer at the bottom left, and we have the hydrophone at the bottom right. But correlating noise loggers are designed to do the same thing. If both loggers can hear a leak, what that means is that they can correlate, they can measure the time it takes for that leak noise to reach the sensor, and they can tell you the distance between the two sensors where that leak is at. So they're very, very useful for pinpointing where those leaks are in the network. So now what we're saying is that you can actually sit in your office and you can see where the leaks are in the network, which is fantastic. But now you've got to think about, again, we've spoken about the amount of data that's coming in. So now we start adding even more sensors that are all sending alerts in, and we're bringing even more data into the equation as well. You know, you imagine having 1,000 of these noise loggers out. How are you going to manage the information coming in? Well, some of the UK utilities have tens of thousands of noise loggers. I think Thames Water have got something like 30,000 individual noise loggers that are out on the network, all bringing data in. And again, by turning to your smart platform, you can let your digital technology do all the hard work for you. So rather than having somebody sitting there looking at every single individual alarm that is brought in, what the platform will do to you is it will look at all the different alarms coming in and it can aggregate them into incidents. So let's say you've got a DMA, and let's say you've got 5 noise loggers, and the 5 noise loggers can all hear the same leak. What you don't want is all the 5 loggers to send in 5 alerts, and you don't want your minimum night flow alert to go off, and you don't want your pressure alert to go off because the pressure's dropped. What you want is a platform to tell you that all of these incidents are related to one leak and to tell you where that leak is. And not only that, it can automatically generate the work order to send the leakage teams out to investigate so that they can pinpoint where that leak is. So that's how we can use the digital technology to help us with the location time. And now we can look at the repair time. How can we reduce the repair time of leaks? The bullet point that you can see on the left, this is the information that the crew needs when they go out and repair a leak. So the first thing they need to know is, where is it? What type of leak is it? Is it a leak on a main? Is it on a service? Is it on a ferrule? Is it on a hydrant? So that they can prepare the equipment. They need to know the size. They need to know the material. They need to know where it is. Is it in the road? Do we need traffic control? Is it a busy road? Do we need to contact the highway agencies? We need to know what depth it is. Can we excavate it, or are we going to need shuttering? And once you know all that, you then also need to know, are you going to have to shut that section of main down in order to undertake the repair? Because if you need to shut it down, you're going to need to know which valves to shut, and you're going to need to know which order to shut the valves in as well, so that you don't create dirty water. And if you are shutting down, have you got any sensitive customers who are going to be affected by that shutdown? So any dialysis patients, any large users, you're going to want to communicate with those customers before you just shut the water off. And when you look at the information that you need, all of that is already held in the smart platform. You know where the location is because the leak team have booked it in. The leak team have booked the type of leak in. The main size, main material, location, and depth are all in the GIS. The valves that you need to shut down are all in your hydraulic model. And the customers are all in your customer database. And all that information is linked in to the smart platform. So at the push of a button, you can generate the work order for the crew, and it will tell you exactly where the crew need to go and exactly what they need to do in order to get that leak repaired. Okay, case study. This is South Australia water in Adelaide. And these guys were having problems with bursts in the CBD. And obviously, if you have a burst in the CBD, that's going to affect the customer supply to customers. It's going to affect traffic. And so what they decided to do was they decided to set up a smart network to see if they could reduce the number of bursts that they were having in the CBD. And the map that you can see on the right, every icon is a different sensor. And so they installed something like 10 big flow meters around the border. They installed 300 acoustic noise loggers. They also included, they installed 100 smart meters as well, connected to the customer revenue meters, as well as transient sensors and pressure sensors. So they put all of these sensors out, and then all the data starts coming back in. And they chose the View platform to hold all this data to help them make sense of it and to help them analyze. And the main intent of the platform was to try and identify leaks before the leaks ran too long and turned into bursts. And they also wanted to identify if there were any damaging transients in the network. Because if there are damaging transients bouncing around the network, then that's going to stress the pipes, and that's going to cause leaks and bursts as well. And you can see that the results of the project that they undertook were very successful. They managed to reduce the bursts by 50% in the first year. And they're expecting to be able to increase that as they utilize machine learning and artificial intelligence as well. And you can see there that there is a financial benefit as well. So they've managed to save themselves $500,000 Australian dollars a year, just based on undertaking the proactive repairs rather than reactive repairs. So sending the crews out in their own time to fix the leak before the crews have to go out to fix an emergency burst, which is usually at night. And finally, from me, I like this slide because I always think about NRW as being similar to being on a treadmill. You're trying to keep your NRW level. It's great if you can drive it down, but at worst case scenario, you want to keep it level. The treadmill is running at the same speed. So just to keep the NRW level, you've got to keep running at the same speed. The problem is that there are things that will weigh you down, and they'll weigh you down and they'll make you run slower. And some of the factors that make you run slower are transients. I just mentioned transients. If you've got transients that exist in your network and you don't know about it, then there's a good chance that they're causing your mains to break. And unless you remove those transients, then they're going to continue to break and they're going to continue to weigh you down. Poor pipe replacement. So if you're taking an old leaking pipe out of commission and you're putting a new pipe in, then you want to make sure that that pipe is going to last for its design life. You don't want it to start leaking before that design life finishes. Because if you put a new pipe in and it starts leaking straight away, that's also going to make you run slower. And it's the same with leak repairs. If you have a leak repair, if you fix 100 leaks and then 10 of them start leaking again within a month, then you're also running against the curve. You're going to find it difficult to try and maintain your NRW when all those factors are pulling you back. But one thing that does help is digital technology. And what I can say is that in my career, where we are right now with the advances in digital technology, I think this is the most exciting time. And I think we now have the biggest scope to try and drive NRW down than we've ever had before. People are starting to talk about zero leakage. You know, that was unheard of 25, 30 years ago. Is it possible? Who knows? What was interesting when Mai did the poll was that 50% of the people who joined are less than 40. Now I'd say that was young. So I think we've got a lot of young engineers watching today, and I think they're going to be willing to embrace the digital technology to help them on the treadmill, to help them run faster. And I think that they're going to have, the young engineers have now got the opportunity to drive NRW down to levels lower than we've ever seen before. So we're talking about low single figure digits. I think that's achievable. And I look forward to seeing how that all works as we go forward. And with that, I would like to thank you for your attention and welcome questions.
Thank you, Martin. Very clear and wonderfully presented. There is a question on the floor to you from Perry Rivera. How do you manage a client who is underperforming on non-revenue water and accept the solution that you are offering? How can you enhance the client's capacity to self-manage and sustain efficiency after your engagement?
Look, really good question. It's interesting that the guys who spoke last week, one of the main points that they discussed was leadership. And I know that when I've worked with clients on performance-based contracts, sometimes parts of the client aren't that necessarily interested to engage, and it really has to be top down. You know, you can understand it in certain instances where people are generally conservative. They don't want to change the way they work. They don't want to accept that things are changing. But it really needs to be driven from the top. So, and this is something that Guy said last week. So the leadership would be the first thing, and manage a client who is underperforming on NRW and accept the solution. Get them to listen to webinars. That's the only thing I can suggest, and try to increase their knowledge. I hope that's answered your question.
But obviously, Martin, sorry to interrupt, but obviously on the question of sustainability, these technologies can be self-managed, and the client does not need to be reliant on the technology provider forever, right?
No, that's right. That's right. It needs to be, there's two things: organizational change management and knowledge transfer. These are the two biggest things for me for NRW contracts. Organizational change management, because companies have to change the way they work in order to adopt non-revenue water technologies, and knowledge transfer. That knowledge has to be passed on to clients so that they can learn and that they can continue, and they take the baton and they continue to run. So yeah, definitely. There has to be knowledge transfer as part of that process, I would say.
Thank you. Second question from Ian Rogers. What solution do you recommend for identifying and locating leaks on plastic pipes? As you know, we have a lot of plastic pipes in the region.
Yeah. Okay. That's a good question. I know there's a lot of plastic pipes, and I know there's a lot of low pressure systems out there. And my answer to that would be to try and avoid undertaking leakage on plastic pipes wherever possible. And before you say, well, that's not an answer, what I would suggest is a method that I've undertaken in Malaysia, and I know it's also been used in the Philippines and in Taiwan and Papua New Guinea, a diverse range of networks. And the way that we've done it there is that you start where the pressure's highest. So you start the treatment plant, you start at the service res, you go in, you establish your DMA, you find all the leaks, you fix all the leaks, and you push the water down the line. Now, there's two caveats to that. Firstly, before you start the work, you must install a PRV, even if the pressure is 5 meters. Because what happens when you go into the DMA and you plug all the holes in the pipe, the pressure goes up. And if you don't control that pressure, if you don't cap it to a maximum level, the pressure just increases and all the background leakage just runs faster and faster, and the water that you're hoping to push down the pipe gets lost in leakage. So the first caveat is using a PRV. The second caveat is that once you've set up that DMA, it has to be monitored and maintained. You can't then move on to the next one and leave that DMA to run itself, because it won't happen. If you really need to do leak detection on plastic systems, the only way that I'm aware of is one of the authors in the IWA manual, he's worked in this region, and he has recommended using ground microphones. And his rule of thumb is that the ground microphone can hear the leak the same distance as the pressure head in the system. So if you have 1 meter head, you can hear the leak from 1 meter away. If you have 10 meters head, you can hear the leak from 10 meters away. But that's the only way that I can suggest that you find the leaks, and it's extremely labor intensive. Somebody has to go into the DMA and put the ground microphone on the ground every 1 meter.
Martin, a number of questions already here, but we're running out of time. Yeah. So I suggest you pick and choose one more question. The rest you can answer via chat.
Why don't you choose for me, Mike?
Okay, so there's a question on, are there standards in pipe laying to avoid leaks and bursts?
Yes, there are.
And where can they find this?
Yeah, look, the best thing to do, get in touch with me, because every country has their own standards in pipe laying. I've come from Australia, and the standards there are very high. I know that when I worked in Australia, the design life of the pipes that we were putting in the ground was 50 to 100 years. And I don't see any reason why it shouldn't be any different here if we're using the same standard materials, the same quality workmanship, and the same design. But we're running out of time, so please feel free to get in touch with me later.
You do have, sorry, Martin, you do have the questions. You can take a look at them, and maybe during the next few minutes, you can reply via chat to all of these questions that have been fielded to you.
Okay, I'll do my best to get through as many as I can.
Great, thank you very much. Now we have, we'd like to call on the next speaker. Our next speaker is Matthew Kennedy. I need you to, I will stop your share screen, Martin, if you don't mind.
Yeah, sure.
Okay, so our next speaker is Matthew Kennedy, and he is the project manager from Xylem. He's also had quite a number of years of experience in this field. He has worked in several projects across Asia, Thailand, India, Malaysia, of course, currently managing a multi-million-dollar smart water and analytics projects across Asia and Australia. He's managing specifically a project now in Malaysia to improve the detection capacity of leaks and bursts in over 6,000 kilometers of trunk mains. And Matthew has previously worked with CH2 MHIL and Halcros. So please, Matthew, your turn. Thank you.
Thanks very much, Mai, for the introduction. Just give me a moment to share my screen. Okay, So thank you everyone for joining. Appreciate your interest in listening to me talk about transients. I hope you will make it to the end. What I will be talking about is continuing Martin's theme to talk about using digital technology to identify transients so that we can prevent bursts. So the outline of this presentation for the next 20 minutes is to give you an idea of what transients are. Martin's mentioned them a little, but we'll go into that in a little more detail. Identifying how we can identify them, their sources, how we can locate them, and how we can mitigate them. So transients aren't a particularly attractive thing to look at. A lot of this presentation will include graphs, like you can see at the bottom here. This covers time along the bottom and pressure in meters up the side. There will be lots of these. So what is a transient? It's a momentary or temporary event. And for the purposes of this presentation, it's a sudden change in pressure. And sudden in this case is where the onset of the transient is rapid relative to the characteristics of the pipe. And that's typically in seconds or less than a second. Many of you may be familiar with this term as water hammer. And whilst transients are very difficult to see, and we may see the consequences of them, many of you may be familiar with them on your own house piping as the thunk sound that you get when you turn off either your kitchen or bathroom tap. What this thunk sound is the change in momentum from the water in the pipe stopping when you close your tap. And that change in momentum introduces a pressure wave into the pipe. We bounce around inside your pipe network and finally be absorbed. That pressure wave can move through the pipe at some very quick speeds. At its slowest, that's 300 meters per second, up to around 1400 meters per second. So these pressure waves can transition along the pipes in seconds for all but the very longest of pipes. And the impact of that pressure wave in terms of magnitude, this is the only equation I'm going to use in the presentation, can be approximated using what's called Joukowski's equation. Very simply, if you have a flow of water in your pipe moving at 1 meter per second, and you slam the valve at the end of it, if that wave speed, which would be typical for a concrete pipe of around 1,000 meters per second, that will result in a surge in pressure of 100 meters or 140 psi. And that has to be absorbed by the pipe. You can see on the images at the bottom of this slide here, it's effective to concertinaing the flow of water in your pipe. And this pressure wave will bounce around inside your pipe network until it is absorbed. So why do we care about this? It can cause damage to your pipes, either in an instantaneous manner. An exceptionally large transient may burst your pipes at a weak point in the network. And it can also cause, or transients can also cause damage to the network through the cumulative stress of numbers or frequency of transients over time. And so what you might eventually see are bursts like pictured at the top right of this slide. But ultimately, transients can be both a cause of pipe failure and a symptom of it too. So transients can cause bursts and be caused by bursts. And so we care about them at the moment. As Martin introduced the concept of awareness, location, and solution, I'll take you through how we become aware of transients on our network. If a transient occurs and nobody is looking, Does it really exist? Yes, the answer is yes, but it's only until now that we've really been able to monitor and look for them. So here are some images of some recorded transients, and I'll talk briefly about how we might be able to classify them and what types of transients we can get. They can be both negative and positive. So on the top left-hand side, we can see a significant drop in pressure of around 80 meters. Negative transients can cause pipe collapse. If they're sufficiently low in pressure, they can draw water into the pipe, cause cavitation, and be very significantly damaging to your pipe network, since most pipes are not designed for this inward suction pressure versus the typical design for a pipe being for positive surge or high pressures, such as that we can see at the top right. So we may get positive transients, surges in pressure. These can cause pipe splits and breaks. Both of these types of transients can occur at the same time from the same event. As the transient moves around your network and bounces from the ends and branches, you can get positive and negative fluctuations. So you can see both of these effects, and this might be something similar to the bottom left graph on this slide. So we can look at them as positive or negative. We can also classify them from their speed of onset, how quickly we transition from a low to a high pressure or a high to a low pressure. We can also look at them in terms of their frequency. So in the bottom right slide, we can see the occurrence of transients and their magnitudes across a period of several months. And this is where the cumulative stress of transients on the network can be observed if we're looking. Here's some further examples of transients and some of their causes. You may get them from overactive pumps, turning on or off every minute, 2 minutes, 5 minutes or so, surging the pressure and then dropping the pressure. Sometimes these surge pressures that you can see on the central graph here, they're unnecessary. It's excessive energy introduced to the pipes to achieve your end goal pressure, which in this graph is around 60 meters from an initial pressure of 10 meters. That surge pressure isn't needed. And so once identified, we can look to solve that. And we'll discuss that briefly a little later. The bottom graph also shows an example of a very significant drop in pressure to around 0. And often this can go below 0, causing cavitation and water contamination issues. So where can these be coming from? How do we find them? So I've already mentioned pumps a fair bit, and pumps get a fair bit of scrutiny and flack for causing transients. The startup and shutdown of pumps and the speed of that startup and shutdown can introduce very quick transitions in pressure into the network. And depending on your pumping regime, this can be quite frequent. It's also worth considering the sudden drop in pressure that you may see as a result of a power failure. And this can introduce very large negative transients into the network as the pumps suddenly stop. But what is often also requires looking at would be pump check valves, where if these are configured or designed incorrectly, an excessive pressure difference as the pump changes from start to stop or vice versa can cause these valves to slam. And this introduces transients also. We can also see across the network that any other type of valve can be capable of introducing transient behavior, whether it is manual, automatic, such as PRVs or altitude valves at tanks, or whether it is even customer demands for some of the larger customers on the network. Similarly, air valves, when these open and close, particularly during a very fast pipe filling exercise or even normal venting, these can also introduce transients. The theme here is that anything that's happening suddenly is likely to introduce a transient to the network. And the final potential source of transients are from bursts. So when a burst occurs on your piping, the sudden ejection of water from the pipe can cause a negative transient as well. And so we need digital technology to look at these, classify them, and hopefully tell us where they are. So why weren't we able to do this before? To look for transients, we need to be identifying high resolution data. It's not possible with traditional sensing equipment that measures in the minutes. As you can see on the graph below, traditional sensing equipment may record pressure as follows, the red line. Unless we're looking at second resolution or below, we wouldn't be able to pick up the transient pressure changes that you can see on the green line. So this high resolution recording also requires a high or very large amount of data. Martin also mentioned 256 Hertz or 256 readings per second. That's 1 gigabyte per sensor per month. That's hundreds of thousands of times more data than a 15-minute resolution of recording. We need artificial intelligence and digital solutions to analyze this data in real time. No one person can take this on themselves. That artificial intelligence can also classify into different transient types, and with other collected data can feed into pipe risk models. So how do we collect that information? Well, we do need specially designed sensors for this purpose. We need a high resolution pressure sensor capable of recording below or sub-second frequency. We need a specially designed telemetry unit that can cope with the bandwidth of that data and transmit it in real time if we're looking for bursts. Most importantly, we also need very accurate time synchronization so we know exactly when the transient has occurred. And I'll explain this on the next slide, but the reason this is enabled by having high accuracy of GPS time synchronization. So how does that time synchronization help us? If we have a network of sensors deployed across our pipe network at different locations, the occurrence of transients in time can be recorded down to the milliseconds. And very simply, the first sensor to pick up the transient will be the sensor nearest to where the transient or the source of the transient. So in this example here, very simply, we can see that we would expect the transient to have occurred nearest to sensor number 1. But we can improve upon this method of locating transients. This would only give us a very large range of pipe that we could look at. So further techniques can look at the speed at which the transient pressure wave travels along the pipe and the time of arrival at those sensors, along with that information, can be used to more accurately locate the transient. So we would be talking in the region of 100 meters or less sort of accuracy, depending on a lot of different parameters here in terms of pipe size, pipe material, and travel time. This can be further improved using transient modeling, theoretical equations with the inputs of the known pipe details, including losses, and the input pressure data from the sensors. From this, we can use to get much more accurate locations of the transients. So knowing where they are, or knowing that they exist, knowing where they're coming from, how do we go about solving them? So if we've identified the source, we can look into a range of possible solutions relating to that. So for pumps, we would want to look at slowing down the initiation or the start and stop with those pumps. And that can be possible with variable speed drives, soft starters, and flywheels. We can also look at attenuating or absorbing the pressure wave generated by pumps or valves in the network. And to do that, we can use surge vessels or accumulators. like pictured on the right-hand side here. These are often a tank filled with a flexible bladder that can absorb the transient energy. So you can see on the graph how this is attenuated, and the peak transient pressure is lessened. With regard to check valves on pumps, we can look at automating these so that they can anticipate better the startup and stop down of the pumps, so that we don't see excessive pressure differentials across them, leading to slams. We can look at better design or right sized of equipment, better maintenance to ensure that that functions properly as designed. And very easily, we can adjust our valve operating procedures so that they're not too quick. The final turns of the valve, we can slow down so that we don't introduce excessive surges. And finally, we might be able to look at pipe redesign and replacement, but only after other options have been considered. And with these mitigations, we can still, with the monitors, sensors that I mentioned on the previous slides, use the digital technology to assess the effectiveness of these interventions. We can trial them and see if they work. So on the example below, we can see that before the mitigation, we have a high frequency of transients, and after the mitigation, we can show that that has been successful. We can also use the sensors to give us early warning of bursts. So this can mitigate the impact of those bursts by allowing us to respond more quickly, address and fix that burst before too much water is lost. This is possible with transient sensors because often our knowledge of a burst relies, as Martin mentioned, on this being visible above ground and reported by the public. In the absence of that, you may rely on other traditional pressure sensing or your tank levels to know when those have dropped below an alarm level. Sometimes this can take quite a long time for long pipes as they empty, and it may take several hours for you to be aware of that. So in this example here, we can see that 2 transients have occurred, and these occurred at least 6 hours before the in-pipe pressure dropped below what could be considered an emergency level. And with that awareness time, that burst could be attended to much more quickly and helps us mitigate the impact of these on the network. So keeping an eye on the time here and knowing that we're quite close to the end, I'll just move on to a summary of what I've just discussed there. Transients can be hard to identify with traditional methods. We need to use digital technology to know that they're occurring on the network so that we can quickly identify, classify, and locate them. This early identification can lead to proactive maintenance, resource prioritization, and design of mitigations. So you can fix the transient issue before it becomes a burst issue. However, if it does become a burst issue, you can also use the same methodology to identify pipe bursts as they occur in real time, which can reduce your response time. And so to conclude the session overall, Martin wrote this one. Digital technology has arrived. It's here to stay. Machine learning and artificial intelligence will further improve our ability to reduce water loss in the future. And using the IWA digital water report that Martin referenced earlier in his presentation, utilities must embrace digital solutions. There really is no alternative. We can provide some access to that report if you contact us after the presentation. But I will conclude there and allow you now to ask any questions.
Thank you, Matthew. There is a question for you from Rongmo Liu. How to handle multiple transient signals within a pipeline network?
Great. Thanks for the question, Rongmo. Multiple transients in a network, they can be occurring from multiple sources or at multiple different times. How can we handle them? With a distributed sensor network, we can identify multiple sources of those transients so that we will be able to use specific sensors in specific locations to say, this is coming from customer A, this is coming from your pump house. If they're coming at different points in time, we can also use those distributed sensors to monitor how those transients propagate through the network. So how far do they travel? Do we need to be looking at our entire 20 kilometers of pipe? Or is it only the first 2 kilometers that are predominantly affected by this issue? So we can prioritize on location using these sensors and monitoring multiple transients. Hopefully that answers your question.
There's a question, but it's for Martin, whether the IWA manual you showed earlier is available free of charge, or do they need to pay?
I think you will need to pay for it. It's an IWA publication. So I suggest you get onto the IWA website and have a look there. But I think you'll probably have to pay for it.
Okay. Any other questions? Okay, there's a question from Ariel Dayanghirang. How practical is it to monitor transients, noting the limitation of data loggers measuring typically 15-minute sampling? Lowering the sampling period, say, to 1 minute exacerbates battery life of data loggers.
Sure, that's a great question. It's a common issue that we end up discussing. So loggers measuring every 15 minutes would not be capable of picking up the true frequency or magnitude of the transients in your network. You may see their consequence as the pipe breaks. If you reduce that sampling interval to 1 minute, you're still not going to pick up the extent or the magnitude of those transients. If I very quickly roll back a few slides in the presentation, we can see this on some of the charts from this slide here. So the green chart, or the green line in the middle, is what would be recorded at a roughly 1 minute resolution. And on that chart, we cannot see the spikes that are pictured in the white graphs at the top and at the bottom. So a 1 minute resolution wouldn't be sufficient. We have to be monitoring at second frequency. And so to address the second part of that with regard to battery life, yes, this does result in a greater power demand on the sensors, but modern technology now allows this to be done with low power, with relatively small battery footprints. Sensors can be lasting for continuous transmission of data. Sensors can be lasting up to a year or more. For summary data, it can be lasting even longer. And of course, this can be further supplemented with solar systems, larger batteries. And we have found effective ways of deploying that around the region as well on the projects that we're currently delivering.
Thank you, Matthew. No open questions, but I would like to ask a question.
Mike, can I just jump in very quickly?
Yes, please. Go ahead.
Look, just to clarify, the IWA manual that we were referring to earlier, the leak detection manual is £85 but the digital technology manual, the digital technology report from the IWA is a free download. So I just wanted to clarify that.
Excellent. Okay, so before my question, Matthew, I don't need to ask it yet. There's another question for you from Will Jem. Can PRVs absorb transient pressure during step test activity?
So we have seen a number of cases in our monitoring about how PRVs respond to pressure. Often a transient pressure wave may be occurring quicker than a PRV can respond. But what we do observe with PRVs quite often is that these can be a source of transients into the upstream network as they try to hunt around a static pressure for the downstream. network. Some of the benefits of monitoring this high resolution transient sensing is that we can also record how effectively these PRVs are working, whether they have failed or not, and whether they are introducing more issues to the network than they're solving. So can they absorb transient pressure during step test activity? I haven't seen examples of step test activity introducing transients with PRVs on the network, would be the honest answer to that question.
Thank you, Matthew. So for my question, I wanted to say that most of the people in the audience are working for utilities that are, let's say, in sizes of 20,000 connections to about 30,000 connections, more or less. Does it make sense for them to also get into the digital technology, considering the costs? Will the benefits outweigh these costs for them?
It's a great question, and some of that may be relevant to Martin's presentation. But no matter the size that you're looking at, if you're facing problems with NRW and leakage, this should reduce the amount of time and help you prioritize where to assign your resources. If you have a pumping station, if you have, it could be introducing transient issues to your network. And so to identify and address those would be to ensure a longer lifetime for your assets. So that's the same problem regardless of the size of utility that you're working at, would be my opinion.
Thank you. And more questions to you. When the sampling time is set to very small, say 1 minute or less, the result is often very noisy. How can I tell if it is a true representation of the pressure or flow rather than noise?
Sure, and it's a very interesting question. I've spent a lot of time looking at pressure plots, rather more time than I should ever have when I graduated university. And
we've lost you, Matthew. Unfortunately,
we can get noise introduced as pressure signals into the network.
Matthew, sorry, we lost you for a bit. Can you repeat your?
Sure, I'll start again. So I remind myself of the question. The noise in the pressure signals.
Yes.
Yes, so we do observe quite a lot of noise in the pressure signals. This can be introduced to the network via, say, vibration from traffic above pipes, pump vibration as it's running, and various other sources. How can we tell whether it's a true representation of the pressure or flow? What we're looking for with the transients is often a relative change. So this doesn't distract from, if there is a change in that pressure, a very significant change, the sensors are still capable of picking that up. If we're looking for an absolute truth in the pressure reading, this is a very similar problem to measuring the length of your coastline as a country. The smaller the measurement tool you use, the longer it gets. It's very much the same with measurement with pressure. So the closer we look, we see other interesting patterns, and this may lead to other areas of research. That noise could be something very interesting to look at. There's a lot of data to look at there.
Thank you. And a final question, standalone high-speed pressure loggers will assist to identify transient cheaply. Sorry, that wasn't a question. I believe that's a comment from Stuart Stapley.
Yes, I hope Stuart should know this. Yes, they should help to identify transients cheaply. Some of the alternatives to identifying them may be to carry out hydraulic modeling analysis and design analysis for your pipes. But that being theoretical doesn't guarantee the presence or the accuracy of that transient calculation.
Okay, well, thank you, gentlemen. I'd like to close the session, but before that, we still have a poll as well as a summary from our Waterlinks board chair. May I start with the poll, please? You have just a minute or maybe 30 seconds to answer this one question. Appreciate your support in responding so we can improve on our webinars in future. A few seconds left to those who have not yet responded. Quickly. Okay, so summary of the poll. Thank you. We have, thankfully, we have matched expectations, and some have said that it has exceeded their expectations. May I call now on the chairman of Waterlinks, Arjun Tapan, to deliver the closing remarks as well as the summary of discussions. Thank you.
Thank you, Mai. Both Martin and Matthew have made exceedingly competent presentations on leaks and bursts that are at the heart of the physical losses that our water utilities experience. So a big thank you to both. There's nothing for me to really add except to say that this subject is key to addressing the problem of exceptionally high water losses in urban Asia. 10 years ago, it was estimated that Asia lost about 29 billion cubic meters of treated water annually. And I think it's safe to assume that this number has increased. And I say this for two reasons. Firstly, very little has been invested by governments by way of non-revenue water management projects. And secondly, the existing pipe networks have aged by another decade, meaning more leaks and more bursts. So the key question is, can our economies really afford to lose anything between 30 and 40 billion cubic meters of treated water every year? I think we should remember that a country like the Philippines, their annual consumption is about 80, 85 billion cubic meters per year. So we're talking about half the consumption in the Philippines. Most cities in developing Asia are unable to provide 24/7 service to their customers. And there are all kinds of wasteful coping mechanisms that have sprung up in response. So the hard reality really is that water insecurity is holding back the rate of growth of developing Asia. I think our water utilities have to set their sights on very clear and quick reductions in water losses. As both Martin and Matthew have shown, the technologies to identify leaks and bursts in near real time are freely available. And using them to prevent water loss, to provide better service, and to improve your financial bottom line is what our water utilities ought to be aiming at. Thank you very much for having joined us today. It's been an educative afternoon. For those of you who are interested in going through the presentations in more detail, you will find them on the Waterlinks website. You will also find them on YouTube and Facebook. Please do join us at the same time on Wednesday, October 7, for our next webinar on commercial loss management. We look forward to having you with us on that date. Thank you very much and good afternoon.